welcome to Programming Like It's 1979. I spend a lot of time on this channel playing programming games, essentially. And today I found something that I wanted to share with you. It's not quite a game, it's a didactic tool meant to be used as part of a class on teaching an introduction to computing. Now, this tool is from the 1980s. I actually used this in my data structures and algorithms class a long time ago. It is called Turing's World, not to be confused with the game Turing Complete. This was a piece of software for the Mac that came along with a book by Jon Barwise and John Etchemendy, and it's pretty interesting. So we're not going to go super in-depth today, but we are going to look at what it is and what you can do with it. So let's go ahead and launch the app. We get a lovely little splash screen, and we're left with a state diagram. So what is a state diagram? Well, a state diagram can be one of three types of machines, either a Turing machine, a finite state machine one way, or a two-way finite state machine. And they have alphabets. We're going to use the default alphabet in this first little experiment. And the default alphabet just has really two possibilities. It has a star or it has nothing. So what does this alphabet mean? Well, at the bottom of the screen here, you can see we have all these boxes. They look a little like memory, don't they? Well, they kind of are. They represent paper tape. The Turing machine is a machine that has a read-write head and a paper tape. And so we can move left and right along the paper tape by using the arrow keys, or we can type our valid symbols. I think space does a blank, so we could do a few stars and then blanks. Let's do a run of 5 stars here. Now up here, we have a palette, a tool palette, and we can place a couple of state nodes. So I'm just going to do 2 state nodes. They're already labeled for us. That's very nice. And then we have some other tools. I believe this node with the circle converts one of these into finite state machine related things. And this will let us draw an arc between 2 nodes. All right. So we need to decide what do we do, or what character is this arc, this state transition, acting on? Well, it's going to act on our star. And what is it going to do when we reach a star? Well, we can move to the left or right, or we can output a letter in our alphabet. We'll output a blank. We're going to make a state machine here, or a Turing machine here, that just erases blanks from a paper tape. So now we have that. I think we can move this arc, can we? There we go, yeah, that's nice. Let's make it a little rounder. Let's make another arc going back to our initial state. And here, as long as we've got a blank, we want to advance the tape. And come on, I want to pull that down. There we go. All right. So we could also add annotations, to our Turing machine. All right, so let's adjust to the notional beginning of our tape here, and then let's run our machine. So we have a number of options for running. Lightning run will immediately move to the end of whatever you're doing. Since this machine, I think, won't actually terminate, I don't want to do that. We could also step through, or we could do what's called a graphic run, which is run it slowly enough that I should be able to see what's happening. So we're going to do a graphic run. And we can see we are now erasing the paper tape. And we've reached the end. So that's great. Right, we're in, and the reason we got that beep is we reached this first node, and I said it was going to run forever. I was actually mistaken. There's no state transition in this node. Nothing tells this node, what do you do if you reach a blank? So let's look at some of the more complicated state diagrams. 4 A's or 3 B's. We're not going to save that. Ooh, look at that. Isn't that nice? A non-deterministic finite state machine. So if we go up there, we can see it's a one-way finite state machine that accepts any string containing 4 A's in a row or 3 B's in a row. Okay, well let's make a tape that doesn't contain that, and let's see what happens. Let's do B, B, A. Okay, and then let's move back to the beginning of the tape. So this should fail, right? And this time, instead of doing a graphic run, let's step through it one at a time. So I'm going to do Command E to step through. So you see that this node just turned black. We've seen 1 B so far, and that's correct. We're going to step again. We expect to move over here to where there's 2 B's. We kind of pop a new level in our state machine. I think that's what's going on there. Now we're moving there. So now we're going to get an A. So what I expect to happen is there's no A edge out of this node. And so I expect it to kind of pop back to here and then walk over here. So step, we popped back to here. This is the active node. Right, that beep said that we couldn't do anything there, I think. Same thing, now we're back here. Now we're over here. Now we're going to get a blank. There's no blank edge coming out of this node. So we're going to hear that beep again. All right, now we're back here and we're on a blank. So what happens here? There is no blank coming out of this node. Let's see what happens. String rejected. So our finite machine is going to accept or reject strings. So what is it? 4 A's or 3 B's? We'll do it like that. Right. And you notice, by the way, that we're not using stars here. That means the alphabet has changed. You can define your own alphabets for use in your state machines. All right. So now we've got a nice long string which ends in 3 B's. And you know what? Let's add a couple of A's on the end there just to see if that makes a difference. We'll do a graphic run. We watch the states unfold. We get that nice audio cue. And this is interesting. It did continue processing until all of the non-blank characters were gone, and accepted the string because there was at least one state that had gotten there. So that's kind of interesting to me that it continued on after reaching this state. I guess that's what this, okay, so that's what this target button is. The target button, I believe, converts any of these into, I guess, a terminating mode. I haven't gotten to that chapter in the book yet. I just pulled this down last night. That's it. That's what I wanted to show you about Turing's world. So what do you do with this? Well, if we look at, this screen's going to go blank here for a minute. The book itself is rather hard to find. I went looking for my physical copy of this book, and I had lost it years and years ago. But you can borrow it on the Internet Archive, and you can borrow it for an hour or 14 days. And the book contains a large number of exercises for you to create your own Turing machines and finite state machines. So if you're interested in an introduction to computing, this is a pretty cool way to do it. You can see we've got an encryption exercise, build a decoding machine for that system of encryption. Let's go back to one of the earlier exercises. Design a Turing machine that will simulate action in the food chain. Imagine that a bee always eats any A that it's facing and moves forward, taking its place. This is Turing's world. Very obscure software. I remember telling people about this years later when I had kind of forgotten that it existed, and I half remembered. And I go up to people and say, do you remember this Mac software that like simulated a Turing machine? And no one knew what the heck I was talking about. And so to stumble across it and find it again is really, really satisfying. And I'm quite glad I did. The same authors also did another book, and I'm going to get this wrong. It's called Tarski's World. And let me look up the description, because I know if I try and describe it from memory, I will get it wrong. But Tarski's World is very similar to Turing's World, but instead of being a finite state machine, it's a computer-based introduction to first-order logic of the sorts of things we were doing in the Incredible Proof Machine and the like. So maybe I'll go see, go trawl on the Internet Archive and see if I could find a copy of Tarski's World, and we could take a look at that some other time. Thank you for joining me. This has been Programming Like It's 1979. Thanks for watching.